Our next topic is going to be the life cycle of a domain object. In this topic, we are going to concern ourselves with the different stages through which a domain object goes, from creation to retirement or removal. First, the domain object will have to be created. There are different ways of doing that. The simplest one that you will be familiar with is just through a constructor. Eventually, the domain object will have to be deconstructed. The simplest way to do that is the deconstructor. In between, the domain object may need to be stored and then reconstructed, or it may need to be communicated over the network or whichever other means, and then reconstituted or reconstructed. So this is what we're going to be concerned with in this topic. I've already mentioned that every object is initially born, it is created in some way. Then it goes through various states and eventually it dies. There are transient objects that do not have a very long lifetime, and for these objects, these stages here are comparatively simple. So we create them by a call to a constructor. Then the transient object is used, maybe just in one computation, maybe in a few, but the idea is that it is used over a very limited amount of time, and then it is abandoned to the garbage collector. We call a deconstructor on it. So this is what we do for transient objects, for objects that do not live for a very long time. Other objects, particularly those that represent entities where persistence over a longer time or longer lifetime is important, those go through more complex life cycles. They also have more complex relationships to other objects, and they have more complex state changes, and they need to satisfy invariance throughout their lifetime. So we're going to be mainly concerned with these objects that have a longer lifetime and how the different life cycle events or the different life cycle stages are represented in software. This state diagram illustrates the different states that are relevant to the life cycle. For example, we create the domain object initially. It is active, whatever it has to do while it is active. We may modify it during the time that it is active. We may want to store it and transform it into a database representation. Eventually, we may want to reconstitute it in order to continue working with it. After a few cycles of this, it is very likely that we either need to archive it or that we entirely want to delete it. There are various challenges that we face when we look at the management of the life cycle of domain objects. One of them is the maintenance of the integrity of the object throughout its life cycle. What's meant by this is the maintenance of the various relationships from this object to other objects, the ranges for the values, associations, links, pointers in the implementation to other objects, to other implementation objects that represent domain objects, and so forth. Another challenge is to prevent the model from getting swamped with life cycle management aspects and the whole complexity that this brings in. There are patterns that help us with that. One of the patterns is aggregates. With aggregates, we no longer view the object boundaries as the top-level boundaries for representing a concept from the domain or a domain phenomenon. Instead, we realize that there might be several objects that together, as a whole, represent a domain concept. We will look at some examples in due course. Another pattern that helps are factories. With factories, we can create complex object arrangements, entire aggregates where several objects together represent a phenomenon or a concept from the domain. These factories have no other purpose than the creation of the aggregate or of the complex object, as opposed to having the object be the host also of the code that is responsible for the creation of the instances of that class. Yet another pattern that helps are repositories. With repositories, we present an interface that is dedicated to querying for the type of aggregates that we have, that we're storing, and we are also delegating the responsibility for the reconstitution of those aggregates to the repository. We will look at this in more detail as we progress through this topic. Factories as well as repositories operate on aggregates, and they encapsulate the complexity of specific lifecycle transitions for these aggregates for us. Let's look at the motivation for aggregates. Assume that you're deleting, for example, a person object from a database, and that may trigger the deletion of the name of that person, the birth date of that person, the position in the company of that person. What about the address where that person lives that we have on record? Should we delete it or not? Well, we might decide to delete it, but it might be shared. It might be an address, a large building where several people live that we have in the database. If we delete it and it's shared, we will be left with a dangling reference in other objects that we still have stored in the database. If we leave it in, but it becomes unused, it is garbage in our database, and that's also undesirable. This seems to be a technical issue, but it really is a modeling issue. The modeling issue at hand is that we need to clearly delineate what belongs to a model object. And in the context of concurrent access, this can lead to acute errors, inconsistencies. So we realize that it is difficult to guarantee consistent changes in a model that has complex associations. We need to maintain invariance over closely related groups of objects. If the objects in our implementation represent together a phenomenon or a concept from the domain, and those concepts and phenomena need to satisfy invariance, then that translates to invariance over some arrangement of implementation objects. And obviously, it is difficult to know precisely at all times which of the implementation objects are involved in the representation of the domain phenomenon or concept. To continue, we can observe that if we are too cautious in our locking, we're locking too aggressively, then we will end up with a slow system, because a lot of it is going to be locked at any point in time. So the question is, how do we know where an object made up of other objects begins and ends. Or put another way, if we're looking at it from the perspective of domain concepts and phenomena, how do we know by looking at the implementation which objects together represent a domain phenomenon or a domain concept? Now it looks like a technical problem at first, but it is rooted in the model. The lack of defined boundaries is the issue at hand. An aggregate is a cluster of associated objects that we treat as a unit for the purpose of data change, for the purpose of the application of invariance and so forth. Think of it in this way. You possibly need several more fine-grained objects in the implementation that together represent some kind of whole from your domain, from the sphere of modeling. Every aggregate has a root. The root is that entity through which all references from the outside need to go. So this is, if you want, the primary object that makes up the representation of the aggregate, the root. All the responsibilities that are accessible to the outside of the aggregate are represented in the aggregate root. And so all calls and all other references to the entire aggregate need to be addressed to the root. And we have a boundary around the aggregate, and the boundary just defines what is inside, what do we consider to be inside the aggregate, and what do we consider to be not part of the aggregate. The objects inside the boundary may hold references to one another. So there's no requirement that they all go through the aggregate root. Since we assume that the participating objects of the aggregate represent a larger whole, it is natural to allow the objects that are considered to be inside the boundary of the aggregate to refer to one another. For the entities other than the root, we only need local identity. The reason for that is that these entities can never be referenced from the outside, and so there is no possibility to confuse them with entities that are participants in other aggregates. So a local identity is sufficient for these entities. So let's look at an example. The example is a car in an auto repair shop. Quite obviously, we're going to treat the entire car as an entity having global identity. If we look at two cars, then we want to be able to distinguish them if they're different cars. Also, we need to track each car through possibly many different state changes. It has a persistence to it that we want to track, and so for that reason also it needs to be an entity. So assume we want to track the rotation history of tires. We have 4 tires on the car. We need an identity of the tires because we want to keep track of how many miles each tire has run in what position on the car. So each of the tires needs to be an entity. But if we assume that these tires are going to be mounted on the car and then they're going to be rotated on that car, and they're never going to be recycled or put on other cars, or if they would, we wouldn't be interested in tracking their history anymore. So if this assumption holds true, then we only need a local tire identity in order to track the rotation history and the mileage in each position for each of the tires. Quite obviously, the car becomes the root entity, and the entire aggregate encloses the tires. Now, what if we look at the engine? How should the engine be treated? Well, it's not uncommon for an engine to be replaced in a car. An engine might be swapped into a different car, might be recycled in a car. So the engine, and it has its own, in the real world, the engine has its own number. And these are all indicators that we might want to treat the engine independently, and it becomes the root of its own aggregate. This class diagram illustrates the relationships between the domain objects. We have the aggregate root here for the engine. The annotation aggregate root in this stereotype notation indicates that this is the aggregate root. We have an aggregate root for the car being the aggregate root of an aggregate. That aggregate encompasses the tires, the positions, and the wheels of the car. So if we decide that the tires are entities within the aggregate, then these tires need local identity only. Similarly for the wheels. The aggregate root is usually drawn if we draw these boundaries, the aggregate boundaries. The aggregate root is usually drawn as sticking out of the boundary of the aggregate, like we did here. Invariants are conditions that need to be maintained throughout the execution of the program, in particular whenever data changes. Invariants involve relationships between members of the aggregate, and it is usually enough if we enforce them with the completion of each transaction, because we can assume that between transactions the data within the aggregate will not change, and so therefore with the completion of each transaction it will suffice to verify that the invariants hold. In this diagram I have annotated some invariants. They're usually annotated in curly braces. So we have the invariant on the tire that the mileage must be the sum of the positions in which the tire has run. To clarify this some more, let's assume that for every tire we have a collection of positions in which this tire has been mounted, and we therefore want the total mileage on the tire to be equal to the sum of all the positions in which the tire has done any mileage. Another invariant we have here is that the time periods must not overlap on the same wheel, and this comment here just indicates that we could check that the invariants are maintained in the rotate method. Of course, this assumes that the aggregate does not change between calls to rotate, meaning that there is no change in the position of a tire other than the change that takes place upon calling rotate. So this is the only entry point that will make such a change. In this case, it will, and of course under the assumption that we do not need to account for hardware issues where bits might flip and so forth. In that case, it is sufficient to check the invariant in the rotate method, because that would be the logically only point where changes could occur. And so it is sufficient to check that the invariant holds after such a change has occurred in the rotate method. Aggregates also mark the scope where invariants need to hold. So not only are the aggregates a compound in a way that represents a domain phenomenon or a domain concept, but as a logical consequence, aggregates are also the scope where invariants need to hold. Let's look at a few rules for implementing aggregates. Remember that there is no direct implementation support by the programming languages for implementing aggregates. So this boils down to us applying discipline in order to implement the aggregate boundaries. The first thing we need to look for is that the root entity has a global identity. The root entity must also be responsible for checking invariants. All entities that are inside the aggregate need to have only a local identity. They must have an identity if they're entities, but that needs to be only local if they are inside the aggregate and not the aggregate root. We need to ensure that nothing outside the aggregate boundary can refer to anything inside except to the root. And the root may give out transient references to some internal entities, but the outside objects cannot hold on to those references. The idea is that we're weakening the boundary just a slight bit in order to allow outside objects to process an internal entity, but that would be a transient reference, so it would only be valid for immediate consumption, so to speak, and not for storage and later reference. The root can hand out copies of value objects. That should be obvious. If we're creating a copy of a value object, then it will no longer have any relationship, any association to the aggregate, and therefore any outside object can do with this value object as it pleases. Because it holds on to a copy, it's not going to affect the aggregate itself. If we're searching for example, using a database query, then we can find only the aggregate roots directly. If we would break this, then we could gain access to the internal entities, and we would shoot ourselves in the foot. That would kind of defeat the purpose of having aggregates in the first place. All other objects are found by traversing associations, and this is done on behalf of the aggregate root. And to the outside objects, the aggregate root represents the entry points with which these other objects inside the aggregate root can be found and can be accessed. Our delete operations must remove everything within the aggregate boundary at once, and any change within the aggregate boundary needs to satisfy the invariants that we have identified for the aggregate. So in order to use aggregates, we want to cluster entities and value objects into aggregates based on how closely they belong together. and we want to define precisely the boundary around each aggregate in order to know what belongs to the aggregate and what does not. We need to choose one of the entities as the root of each aggregate. That will normally be quite a straightforward choice. In the typical case, there's not much in terms of choosing. There will be one entity that stands out as the primary entity of the aggregate, and we choose that as the root. We want to control all access to the objects inside the aggregate through that root. External references are allowed to go to the root only. So that in turn means that the root must provide all the functions for the entire aggregate, even if those functions are then implemented by some entity within the aggregate. Even if it's a single entity within the aggregate that is responsible for the implementation of that operation, it is still the aggregate root that makes this operation accessible to the outside of the aggregate. We can have transient references to internal members. They can be passed out for a single operation. The purpose here is to allow for a performant implementation while slightly breaking the boundary of the aggregate temporarily. And all this makes it practical to enforce the invariance on the objects that are inside the aggregate and on the aggregate as a whole. We can implement these invariants, the checking for the invariance, in the aggregate root, and the aggregate root will be responsible to know when the invariants need to be checked. Or put another way, the developer needs to consider when the invariants need to be checked and needs to place these invariants within the aggregate root in such a way that in the crucial points the invariants are checked. We're next going to look at a little more extended example involving purchase orders. The idea here is that we have a purchase order, and on that purchase order we have an approved limit as to how much money can be spent. The purchase order is then going to be made up of any number of line items. Each line item specifies a quantity and has an association to a part, and the part has a price for the individual part. The invariant that we want to satisfy on these classes is that the sum of the item amounts is less or equal than the approved limit of the whole purchase order. Here are a few sticky points with the diagram that we saw on the previous slide. The first one is invariant enforcement. We might decide to check for each line that we have added, but if we check the invariant after adding the line, then the invariant will already be invalid if the total goes above the limit, but we have added the line. So this seems to be the wrong point in the whole process to do this check. Another sticky point is change management. Let's say we're deleting the purchase order and that deletes all the line items, but we have no guidance from the previous diagram as to when to stop following relationships. Should we delete parts as well? Very unlikely. Then there is the issue of the impact that changing the part price might have at different times. What is the impact if the part price is changed before we add an item to the purchase order? What is the impact if we change the price after we have added that part, that item, to the purchase order. These are things that need to be considered, and we have no guidance from the diagram on the previous slide. The next and last one on this slide, the next sticky point is sharing the database. If we lock, for example, the parts, then we obviously run into contention problems when we have multiple users, some wanting to access the same parts, or some users wanting to update a part while that part is being used in a purchase order, and so forth. We're going to look at various strategies for resolving these issues. In this first one, we're assuming that we will lock any object that a user begins to edit until the entire transaction commits or aborts. With this assumption, or with this strategy, what happens when two users edit separate line items on the same purchase order? The scenario here is that user 1 enters a 5 for the quantity of guitars. We are under the assumption that previously there were only 3 guitars. Each guitar costs $100, so 5 guitars, that's a total of $500. 2 trombones, again, the assumption is that there were 2 trombones before the edit, 2 trombones for a total of $400, and we are within the approved limit of the purchase order. User number 2 does something similar, also starts with 3 guitars and 2 trombones, but changes the number of trombones, in this case to 3. So this purchase order here is also within the approved limit. But the resulting purchase order will not be within the approved limits. The reason this can happen is that we lock any object that a user begins to edit until the transaction commits or aborts, which means that since user A or user 1 only edited the first item, the first line item in the purchase order, and user B only edited the second one, there was no conflict initially. There was no conflict during these edits, and we only see the conflict once both of these edits have completed and the transaction commits. To clarify this some more, the assumption here is that as soon as user 1 edits the quantity of this line item, we lock that line item, and the same happens for this line item here. In our next strategy, we assume that we are locking the entire purchase order, not just the line items, but the entire purchase order. Quite obviously, this would prevent what we saw on the previous slide to take place. But now, as long as the first user edits the purchase order, the second user remains locked out. Then, when the first user committed, the second user gains access and can only commit when the invariant is satisfied. So what we have on the plus side, the advantage of this is that we are making sure that the invariant will be satisfied. But the problem obviously is that the second user remains locked out for possibly an extended amount of time. In our third strategy, we want to take care of the possibility of the parts changing prices while we are preparing the purchase orders, and thereby allowing us to commit a purchase order that no longer satisfies the invariant, because in the meantime the prices of the parts may have changed. Now, if we do that, if we lock the part while we are composing a purchase order, then we can easily see that this can lead to deadlocks. The example, or one example that shows that, goes like this. We have two separate purchase orders, and each has its own approved limit. And in the one purchase order, we have already added guitars and trombones. So we are locking guitars and trombones. In the other purchase order, we have added violins and trombones. Violins, and we're trying to add trombones. But trombones are currently locked by the first purchase order, and so we are not going to be able to conclude or to commit this purchase order before the first purchase order here is committed. Now, if the first purchase order adds violins that are currently locked by the second one, then we have a deadlock, because this purchase order will not be able to commit unless the 13,545 commits, and vice versa. The 13,545 cannot commit until the 12,946 commits. So we have a deadlock. So let's look at some improvements on these previous strategies that we saw. One consideration, or one thing we might observe, is that the parts are used in many places. We are very likely to have many purchase orders being processed simultaneously, making reference to many individual line items, and each one uses a part from the catalog. So this is obviously a high contention domain object. Our second observation is that parts changed rarely in comparison, for example, with purchase orders. And another observation is that part price changes might not affect the existing purchase orders. We might not even want existing purchase orders to be affected by a price change that comes in while the purchase order has already been committed. We might even go a step further. We might not want the price change to affect a purchase order that is currently being composed. That is to say, if a user has started to compose a purchase order, they refer to the prices as they were at the start of composing the purchase order, and any price change that happens while they are composing the purchase order isn't going to affect their purchase order. This is a decision or an observation that we might make. We might say, well, that's how it is in the real world out there currently if we're operating with pen and paper or whatever. As a consequence, we loosen the dependency from a line item to the part by copying the price. So we have a reference to a part, and the part has a price. But when we add a line item to the purchase order, we copy the price from the part, the price as it was at the time of copying. And in that way, we loosen the dependency from the line items to the parts. Now, to deal with part prices, part price changes, we might put together a list of recently updated part prices at the end of the day, and that might trigger a review of purchase orders that were put together based on prices that did change during the day. This, of course, avoids contention. We can just copy the price. We just need to access the part. There's no need in locking the part for an extended amount of time. And it may reflect normal business operations better. Normally, when some transaction is being composed, being put together, we do not expect any changes that take place while this transaction is being put together to affect that transaction, the outcome of that transaction. And the aggregate that we have introduced here now ties together the line items and the purchase order. Both of these form the aggregate, and there is a reference to parts, and parts are outside of the aggregate. And this is as it should be. We're going to talk about factories now. First, some motivation for using factories. Consider the problems that arise from overloading a complex object with the responsibilities for its own creation. An analogy would be a car engine. There are obviously many parts that collaborate in a car engine to turn the shaft, but the car engine does not have the responsibility to assemble itself. This is a responsibility that we consider to be completely unrelated to the purpose of the car engine itself. In a similar vein, we can consider assembling a complex compound object to be a separate concern from the use or the purpose of that same object itself. One approach could be to shift the responsibility for creation to the client. But in that case, the clients need to know the internals. They need to know the invariants, they need to know the rules, and so forth. If we would do that, we could no longer change domain objects without changing the client as well. And so we would have a breach of the domain objects and the aggregates boundaries, the conceptual boundaries. And if the client would be a client on the application layer instead of in the domain layer, we would even leak domain responsibilities into the application layer and domain knowledge into the application layer, which is also something that we do not want. The creation of complex objects is a responsibility of the domain layer, but not of the objects of the domain model, at least not of most of the objects of the domain model. There are some object creations where the creation of the object does correspond to an important domain event. For example, when we talk about opening a bank account, that clearly is a domain event and is meaningful on the domain level. Whereas in many other cases, the creation of the domain object is not something that we would talk about when we talk about the domain model. So it doesn't reflect something that we want to explicitly model in our domain model. In those cases, the object creation itself has no relevance for the domain model. We will therefore add constructs to the domain design that are not part of the domain model. So in that sense, we are breaking our rule that in our domain layer, we have only those things that are directly forced to be there by the domain model. But they do fulfill an important responsibility for the domain layer, and therefore we do include them. And we call these factories. Factories then encapsulate the knowledge that's needed to create a complex object or an entire aggregate. In order to work with factories, we shift the creation of complex objects or aggregates to a separate object that has the sole responsibility of creating the object or aggregate. And this is possibly a responsibility that is not explicit in our domain model. We will provide an interface for these factories that encapsulates all the complex assembly, and the interface does not require reference to concrete classes of the objects being instantiated. To the contrary, it is good to use some abstract classes here or just interfaces. The entire aggregate needs to be created in one piece so that it ensures the invariance from the start. And the actual implementation of our factories can use the factory method, the abstract factory, or the builder pattern. You can read up on those in more detail. We will be concerned with when and why to use factories, not the details of their implementation. So what are some necessities? What are things we need to ensure to use factories? One thing we want to ensure is that the creation methods are atomic and they enforce all invariants of the created objects or aggregates. What we mean by atomic here is that we do not get some intermediate state back from some method that we then use to build the final object from, in which case we would have access to some non-usable state. This would defeat the purpose of having factories. So we want methods that in one simple call, in one single call, create a valid object or aggregate that we can then use, and that ensures all the invariants. Obviously, all objects produced must result in a consistent state. And when we create an entire aggregate, then all the invariants need to be satisfied, and it's possible that there are optional elements that can be added later, but the elements that need to be there, they all need to be there, and they must satisfy all the invariants. If we have any immutable value object attributes, then these must be initialized to their correct final state. If the interface allows calling what would produce an impossible object, meaning if there are calls possible in the interface to the factory, that would lead to the method not being able to construct a valid object. In that case, we must use exception mechanisms or other mechanisms to signal that an impossible state would arise, and the caller will have to deal with that possibility. The factory should be abstracted to the desired type, and it should not need to use any concrete classes for the objects created. Let's consider the choice of where to host the factory. Where should the factory find its home? In the case where we are adding elements inside an existing aggregate, we can easily implement a factory method on the aggregate root, on the entity that is the aggregate root. In the example here, we have a purchase order and we have a method on purchase order which is called new item. So this is the factory method that will produce or create a new purchase order line item. And the purchase order has a collection of the line items associated with it, and it is responsible then for creating another one. This one here is I3, which can then be added to the collection of the purchase order items associated to this purchase order. The purchase item is not the root of the aggregate, so item number is unique only within the aggregate. So we only need a running item number within the aggregate purchase order. Observe here that we are returning the object that we are creating. So we are giving out a reference to an internal object. This should only be a transient reference that we're giving out, which means that the caller who's calling this new item method should not rely on any persistence for this object, cannot rely on any persistence for this object. So it might use this reference, for example, the fact that it's not a null reference to indicate that the operation was successful. For example, that would be a valid use of a transient object. What we're gaining here is that we are hiding the interior implementation of the aggregate from any external clients, and the root retains the responsibility for ensuring all the integrity of the entire aggregate. Another option for the site of a factory would be to have a factory method that is on an object which is itself closely involved in spawning some other object, but is not itself the owner of the product. The example that we have here is the creation of a trade order. In the creation of a trade order, the brokerage account for which the trade order is being generated is an object that is closely involved in the spawning of this trade order, but the brokerage account is not the final owner of the trade order. So it is not the case that the trade order becomes only accessible through the brokerage account. The advantages of choosing this site, this way of placing the factory method, is that it often saves pulling information out of the spawner here being the brokerage account. We do need some information to create the trade order from the brokerage account anyway. So hosting the trade order creation on the brokerage account relieves us from having to pull that information out of the spawner if we were to host this creation in some other place. And another advantage is that it makes the special relationship between the spawner, the brokerage account in our example, and the product explicit. The trade order is not part of the brokerage aggregate, but it is relevant in trade execution. The brokerage account holds information and rules that need to be embedded or applied to trade order creation. And therefore, in this example, it is a good choice for the site of the factory method for trade orders. We can hide in this way the actual implementation of a trade order. For example, there could be an entire class hierarchy, buy orders and sell orders, market buy orders and market sell orders and limit buy orders and limit sell orders and so forth. The actual implementation can be hidden from the client. The factory keeps the client uncoupled from the concrete classes. The client only needs to know about the top-level class or the interface that is necessary. If we have a factory that is tightly coupled to the product, then it should be attached to an object that has a close natural relationship to the product. That is a general guideline. Sometimes we do not have such a host for the functionality for the factory. In this case, we can create a factory object or a factory service, which is basically an object that has no other purpose than to provide the factory method for the product that we are creating. A standalone factory usually produces an entire aggregate, will return the reference to the root, and will ensure the invariance. If there is an interior object that needs a factory, but the aggregate root seems to be unsuitable, then we make a standalone factory, like here. This is a factory service, brokerage account factory service. And of course, we need to respect the rules that limit access in order to respect the aggregate boundaries. In particular, only transient references from clients outside the aggregate are allowed to the result of what the factory creates. For example, the application might call this brokerage account factory, saying we want to create a margin account for John Smith. Well, the brokerage account factory generates the next sequence number, generates a brokerage account as a margin account because that's what we said. We do get the reference to this brokerage account back. If we assume that the brokerage account is not if we assume that the margin account that we have here is not the aggregate root, then of course we would be allowed to pass out references to this margin account object only in such a way that the client uses them transiently and not permanently. So here are a few considerations on when to use factories and when to use constructors. To start, factories are often underused. So consider using a factory. Chances are you might otherwise miss out an opportunity to free up an object, a domain object, from the responsibility of its own construction and make the domain model more easily understandable. You might miss out on that opportunity. But factories can obscure simple objects. So if you have a simple object that just needs to be made and it's obvious what has to go on in this case, then use a constructor by all means. Don't use factories for the sake of using factories. When to use constructors? When the class is the type. When the object or the class is not part of an interesting hierarchy. When the result isn't used polymorphically by implementing some interface or similar. When the client cares about the implementation and so therefore needs to be aware of the specifics of implementation. When the client has all the attributes for the creation available for whatever reason they're already there, and when the construction is simple. A public constructor, just like a factory method, or whatever other method of implementation you have chosen, must be atomic and must satisfy all the invariants of the created object. You want to avoid calling constructors from within constructors of other classes. If you catch yourself doing that, consider choosing a factory instead. And any complex assembly of objects that together form some conceptual whole should use factories. What should the factory interface look like? Whether we're using a factory method or whether we're using a standalone factory service, each operation must be atomic. We need to pass in everything that is required to create a complete product in one atomic operation. And we need to consider what should happen if the operation fails, if the creation cannot proceed. Should a null be returned? Should an exception be raised? Or should something else happen entirely? We need to be aware that the factory will be coupled to its arguments, and so therefore we must take care in selecting which input parameters we should provide and how we can avoid too many dependencies. Typically, if we use parameters from a lower design layer, that is safe, and we can even use parameters from the same layer if there are more basic objects that reside on the same layer. And if we use objects or types that are closely related to the product, then that is usually a good choice, and that doesn't introduce any new dependencies. Remember that the dependencies are conceptual dependencies, so if it is clear that the product is tightly related to some other objects, then using these other types as parameters doesn't introduce any new dependencies, because we already do have the dependencies on the result anyway. And we want to use abstract types instead of concrete classes to be more decoupled than by using the concrete classes. How do invariants relate to factories? It's quite obvious that the factory must ensure that the product that it produces satisfies all the invariants that we have for the product. We do not normally want to take the rules that apply to an object outside of that object. But with factories, what we can do is we can delegate the invariant checking to the product. Even if the product is an aggregate, then the aggregate root might have the responsibility of checking the invariants. And the factory could then call into the aggregate root in order to trigger those checks. If aggregate rules span several objects, it might be the best to place them inside the factory. Whichever way we do this, the invariants need to apply after every operation. The fact that invariants need to apply after every operation does not necessarily mean that we need to check them after every operation. Many operations cannot change whether the invariant applies or not. For example, rules that apply to the creation of an identity for an entity, well, as soon as we have the identity, we treat it as immutable. There are no operations that change this identity. So if we have some rules that govern what are acceptable identities, then we only need to check these rules at the creation of the entity, not after every operation. And such rules may better be hosted inside the factory as opposed to inside the aggregate. Factories are not limited to producing entities. It is also possible to use factories to produce value objects. If we do so, then it's quite obvious that the product must come out complete in its final form. That is because a value object is a value object and it is immutable, and so we cannot, after the creation, add anything to it or change anything within it. So the factory operations in this case need to allow the full description of the product, because there's no possibility of adding or changing anything after the product is created. For entity factories, the situation is different. We can take just the essential attributes for creation of a valid aggregate, and then we can add details later. If an outside identifier is used, it needs to be provided to the factory. So if the identity derives from some outside identifier, then the caller to the factory needs to provide that identity in order for the factory to create the aggregate. If the program assigns the identifiers, then the factory is the place to do it. That is to say, if the identity is created not provided by the caller, but created in the process of creating the product, then the factory would be the place to generate the identity as well. We can use factories in another situation. That situation is when we reconstitute objects. Imagine the situation where you are transmitting or storing an object. Well, for the transmission or the storage, you're flattening, you're somehow encoding the object data in a different format. It's not the same as a live object on which you can directly operate. You are somehow sequentializing it. If you retrieve an object, either through transmission or from storage, then that requires the reassembly of the data you receive or you retrieve into an object onto which the system can operate. And factories can be used for this purpose as well. There is a major difference in this scenario as opposed to the initial creation, and that is that entities do not get new IDs, and therefore the identifying attributes must be part of the inputs to the reconstituting factory. And there is another difference, another important difference, and that is that invariant violation must be handled differently. Imagine that you encounter an invariant violation. Well, if you encounter an invariant violation upon initially creating an object, then an aggregate, for example, then it is very likely that the corresponding aggregate, the corresponding object, just cannot be represented. However, when you are reconstituting a stored object or you're recreating something from a transmission, then that object already existed and you need to be able to reconstitute it. In creation, when invariant violation occurs, you can raise an exception or return a null pointer. In reconstitution, the object, the conceptual object from the domain already exists, and so it has to be repaired. You have to provide the continuity, the persistence that the users expect of the object, and so it has to be repaired. And that might require the intervention of some human users. To summarize the ideas about factories, we need to identify access points for the creation of instances. Those can be constructors for the very simple cases. Those should be factories for more abstract or elaborate instance creation mechanisms. And factories do not normally represent any part of the domain model, but they are part of the domain layer nonetheless. In some cases, as we have seen, for example, the creation of a bank account, the factories do represent a part of the domain model, but that is comparatively rare. Factories encapsulate not only the creation, but also the recreation, the reconstitution, either from transmission or from storage. Our next topic is going to be repositories. Some introduction on the topic. When we are looking for objects, we very often are able to find those objects using its relationships to other objects. The question is, where do we start? What are the anchor points, so to speak, when we are looking for an object and it is in the middle of its life cycle? So we're not creating it and it hasn't been deleted. We are looking for an object that has been created from the perspective of the domain, is alive, and we need to work with it. Well, we need a reference to that object. How do we get that reference? It's obvious if we are at the beginning of the life cycle and we create an object, then from the factory method or the constructor, we can get a reference to that object. We can traverse an association if we're holding on to some objects and the object we're looking for, with which we need to work, has a relationship to that object to which we're holding on, then we can traverse associations to get there. So if we have an entry point, we are fine. If we don't have an entry point, if we do not hold on to an object from which we will find the other object we're looking for through associations, then how do we get the entry point? That is the key question we're going to address with repositories. We can obviously query a database to get an object based on attributes or to find constituents and to then reconstitute the object we are looking for. There is some caution here, that is that database search is globally accessible, and so the developers need to impose discipline on how they access database search in order not to break any encapsulation or aggregate boundaries. Search favors decoupling, traversal of association favors cohesiveness, and so the right combination of these two mechanisms can improve design comprehension. From a technical point of view, we can see retrieval as a subset of creation, but this view is problematic. Conceptually, retrieval is in the middle of the life cycle, whereas creation is at the beginning of the life cycle. So conceptually, we're dealing with very different views or with very different contexts. For example, if you're retrieving a customer from a database, that does not make this a newly created customer, and so therefore, from the perspective of the domain model, these are some totally different concerns. We quickly lose the model focus if our approach to this is that we are creating an SQL query, which we're then passing to some query service in our infrastructure layer, from which we then obtain some result table, from which we then extract data that we pass to a constructor or to a factory. If this is what we're doing, then we're losing model focus. So we don't want to do this from the perspective of the domain model. while this might be going on somewhere, it should be at a considerably lower level. It is definitely not something we should be doing in the domain model. And these technical issues, if we focus on them, they let us think of objects as containers of data. And because of that, we will come to a kind of data processing style where we are no longer thinking of what's going on inside the system as a representation of things that go on, phenomena and concepts and actions that go on in the domain, but instead we're thinking of data and how that data is being processed, which is clearly inferior to thinking of it in terms of the domain. There are more cautions and potential drawbacks. If we're using a database directly, developers are tempted to bypass model features or model abstractions. They're tempted to directly access the database and possibly derive information directly from that database. If that is what's going on, from the perspective of the domain model, aggregate boundaries are not respected. And even object encapsulation gets bypassed. And of course, I mean, the consequences of that could be that we end up having objects stored in the database that do not satisfy their invariance and all other kinds of possible bad occurrences that can result because of that. The domain rules can easily end up embedded in SQL queries. So we do have some rules from the domain, some invariants, for example, and we embed them in SQL queries because we are directly accessing the database. This is also bad design. In order to reduce the scope of this object access problem, we are going to observe the following. First of all, there should not be any queries for transient objects. Well, they're transient in the first place, so they're not persistent. So we should not expect to be able to obtain them from a database in the first place. There should not be any queries for persistent objects that can conveniently be found through traversal. So if it is an object that we can find from some other objects because of its relationships to that other object, then we should not need, or we should not even provide a query for such an object. We should not provide any queries for non-root aggregate members. So only for the aggregate roots should we provide queries. If we do all these three here together, we have much fewer entry points in our database, query entry points. Global search for persistent value objects is often meaningless. Think about it. If you have the information that is contained in a value object to specifically query for that one specific value object, then you might as well create it. You might as well create an instance that has the properties for which you are searching, because they don't have any identity to the further processing. It will be meaningless whether you are working with the one that you could have obtained by querying by global search, or whether you are working with a newly created copy that happens to have the same properties. There are some exceptions of value objects for this is not true, but I'm not going to go into this now. If you find yourself searching for a value object in a database, that might be an indicator that you actually have an entity and you just haven't recognized its identity yet. So the question that you should ask yourself if you're finding that you're searching the database for a value object, you should ask yourself, is this possibly an entity? Does this possibly need an identity? As it turns out, from what I just said, to summarize, most objects should not be accessed by global search. This is where repositories come in to help us with these problems. With repositories, we are providing a subset of persistent objects that must globally be searchable by searching for corresponding attributes. This is needed for the roots of the aggregates that are not conveniently found by traversal. So there are some aggregate roots that we cannot conveniently find by traversal, and that we therefore need to be able to search by attributes in the database. The search targets are usually entities, and in rare cases, they're value objects with some complex internal structure. Free database queries, if they're used in the application, in the source code, in the implementation, free database queries can breach the encapsulation of domain objects and aggregates, and so therefore we need to avoid them. And the exposure of technical infrastructure and database access mechanism complicates the client, and it obscures the model-driven design. So therefore, we want to avoid them. So the database queries, they will be hidden behind an interface that the repositories provide. And similarly, all the technical infrastructure will be hidden inside the repositories. So that for the domain layer, there is an interface for storing and reconstitution that speaks the language of the domain and hides all the technical issues behind that interface. The idea of repositories is that we're dealing with the challenges of database access, with the technical challenges. SQL can be encapsulated into query objects. We can use metadata mapping layers to translate between objects and tables, and we can use factories to help reconstitute objects. But still, we can lose sight of the concepts in the domain model if we are concerned with all these technical issues. We are no longer communicating about the business, about enterprise rules or whatever, but we're manipulating retrieval technology. We're manipulating object relational mappers or whatever. This is where repositories come in to help us. The purpose of repositories is then to have a single conceptual framework behind which we encapsulate the technical solutions, and which at its interface brings back the domain focus, so speaks the language of the domain. Repositories have the following desirable properties. A repository represents all the objects of a specific type as a conceptual set, as a conceptual collection. It has more sophisticated querying than what we typically find in the collection data types. It allows insertion and removal of objects and provides persistence. It encapsulates this insertion and deletion that takes place in the underlying database. To continue, it provides a cohesive set of responsibilities for access to the roots of aggregates. What this means is that there are entry points, and these entry points have a cohesive meaning. They're all concerned with closely related responsibilities concerning the roots of specific aggregates. So obviously we may have different repositories, a repository for clients, a repository for trade orders, and so forth. The clients will then query the repository to select objects by criteria, and this does not have to be completely free form. This, to the contrary, this will typically provide selections that are meaningful to the specific cases that arise in the domain. Selection from the database, metadata mapping, all these things are encapsulated behind the repository. And specific queries based on the criteria that are needed by the client, by the caller, are implemented. So queries that in particular make sense for retrievals that occur from the domain. We can also return summary information. For example, we can count matching objects, or we can compute averages and so forth. These types of summaries might make sense in the domain, and therefore they can be represented in the repository. From a very high-level point of view, the structure is like this. We have a client, and the client communicates selection criteria to the repository. What's important here is that the client asks for what it wants in model terms, so at the level of domain model concepts and phenomena. And the repository provides entry points that are meaningful in terms of the domain. Then the repository encapsulates all the database access technology and strategies and so forth, and it delegates the resolution, so to speak. It delegates that to the database interface, to metadata mapping, to factories, to other repositories, and so forth. So the important thing, or the important point, is that the repository provides the client with an intention revealing interface in terms of the model, in terms of the domain. This takes us to the following guidelines. For each type of object for which we need global access, we create an object that represents all objects as if they were an in-memory collection. So this is our repository. We then provide methods to add and remove objects, and we encapsulate all insertion and removal in the data storage behind this interface. We do provide methods to select objects based on criteria, returning matching and fully instantiated objects or even collections of objects. We provide repositories only for aggregate routes that need direct access. And in this way, we keep the client focused on the model, and we delegate all storage and retrieval aspects to the repository. The advantages of using repositories are that we now have a simple model for obtaining persistent objects. We are decoupling the application and the domain from any persistence technology, whether databases, data sources, whatever. We are communicating design decisions about object access, and we are facilitating different implementations, in particular a dummy implementation that can be used for testing. Repositories and DAOs are closely related, but they're not the same thing. DAOs, data access objects, are typically created per table, so that you have one data access object that represents one table. So there's usually a one-to-one correspondence there. And DAOs are oriented by the database schema, whereas repositories are domain oriented. So here we take a different view. We're not concerned with how the implementation inside the database is structured. Instead, we are concerned with what is required by the domain. And a repository can be implemented by DAOs. Possibly several DAOs would be involved in implementing a repository. I've spoken quite a bit about the querying that we are providing through the repositories. Our repositories allow querying for objects that match some criteria. In the easiest implementation, we would provide some hard-coded queries for that are then fed with specific parameters. An example for that would be to get all the trade orders for a specific tracking ID. So we have a client that calls into this for tracking ID and provides the tracking ID, and this is the method that the repository provides. And the repository then somehow, we're not talking about the implementation yet, the repository then locates and reconstitutes the corresponding object or objects as a collection, if that is appropriate, and returns the corresponding reference to the object or to the collection. Some examples of typical queries that a repository would provide. Retrieval of an entity by its identity. So we already know the identity that we're looking for, and we want to find the corresponding entity. Requesting a collection of all objects that have a specific value for some of their attribute. That's a typical query. Selecting objects based on value ranges for some of their attributes. Performing calculations that are the responsibility of the repository. Those would typically be database-related operations. And last not least, the return of summaries, counts, sums, max, mins, and so forth. So these are typical queries that we would find on a repository. In the case where our application needs more flexible queries than these very specific queries that are parameterized maybe over just one value, in that case, we have one option would be the specification-based queries. What we do in this case is that we have some way of representing criteria, for example, as a criteria class. So this is, in a sense, a sublanguage that we introduce within our application that has the purpose of representing search criteria or selection criteria. So the idea here is we represent this criteria here. We create a new criterion and we specify that this criteria matches the security name with WCOM, and it matches the account with the number 123. Implicitly, these two criteria would be ANDed or together. That depends on the on what you want to represent in your specific application. Let's assume that these are ANDed together. So the client would then communicate this criteria object to the repository, and the repository would have to have the entry point to find a collection of objects for which the repository is responsible, in this case here trade order, that satisfy these criteria. And in our example here, we would have these trade orders that all match, and that would then be placed in a collection, and this collection is passed back to the client. This approach still allows for the addition of specialized hard-coded queries. So it is possible that our implementation of this matching based on a criteria object is maybe not as efficient, maybe not as performant as if we would hard code some queries. We could still have those. We could still have specific hard-coded queries that are exposed through the trade order repository here. This provides convenience for often used queries, and it may also provide increased performance. Also, for summaries, we may not want to first obtain a collection and then pass that collection back to some form of summarizer. So we may want to expose such a query for the summary of selected objects directly. Let's now look at the implementation of a repository. Obviously, the implementation will depend on the underlying technology. That's the whole purpose. That's where these concerns should be addressed. We do want to hide the internals from the client, obviously, or maybe not so obviously. We don't want to hide them from the developer of the client. The developer is, of course, free to investigate how the repository is implemented, but the client does not need any knowledge of that. To the contrary, the client cannot rely on any knowledge of the implementation. The client code will therefore be the same whether we are dealing with an object database, with a relational database, or whether we are dealing with an in-memory collection or in-memory database. The way the application will carry out the querying, the way our implementation will implement a query from the client, well, initially we have the request from the client in terms of the model terms. That goes to the repository, which provides a corresponding entry point. Then in the repository, we can create a query string. That query string can be passed to the database interface. So this is the SQL query string that was created based on the call to this method. And from the database interface, we get a result set in terms of a table. From this result set, we can call the reconstitution method on some SQL trade order factory that has the purpose of creating objects from a result set, an SQL result set. Such an object here created will then be returned to the trade order repository and through the trade order repository to the client. So this is how the implementation based on an SQL relational database could proceed. Now we're going to talk about some guidelines for implementing repositories. First of all, abstract the type. You can use an abstract superclass of a hierarchy. You can even introduce a hierarchy for unrelated or otherwise unrelated types if these do not have a common hierarchy. The database technology that you are using for implementation might give you some constraints on polymorphism here that you need to deal with. You want to leverage the decoupling from the client. This means, if you do it properly, that you can vary the query implementation. You are not tied to a specific implementation of the queries. You can optimize for performance within the repository. You can, for example, cache results. You can switch the persistence technology, for example, for testing. And in particular, for testing, you can use a dummy in-memory implementation strategy for your repository. The repository should not be concerned with transaction control. Leave that to the client. That's important to understand. It's quite likely that several queries, several inserts, for example, or updates that you issue to the repository need to be bundled into one transaction. And the repository isn't going to know which of the calls need to be bundled together. So the client does know which transactions or which inserts or which updates together form a transaction. So the client is the place where you should trigger transaction control. The client has the context and can initiate and commit units of work. You can pass a unit of work carrier, if you want, to the repository, or provide one when you initially create the repository. And then the additions and updates can be collected in the unit of work, and the client then triggers the actual commit. Transaction management in this way becomes much simpler than if the repository would have to find out when the right time for a commit is given. Some more words on the relationship between repositories and factories. Factories are used to create, so they are at the beginning of the life cycle of an object. Repositories are used in the middle or towards the end of the life cycle. Storing objects in non-object oriented systems is possible. For example, you can store the objects into files or relational databases. But in order to use these objects then in your object-oriented application, it requires reconstitution of the flattened out representation in order to arrive at an object that the application can use. If you look at it from a purely technical point of view, then a repository acts as a factory in this case for the reconstitution. But from the model level, there is a difference that we already talked about a little earlier. Factories and repositories have different responsibilities, and therefore we want to distinguish them because from the model perspective, they serve different purposes. The client should have access to the repository as if the objects are stored in memory, as if it is accessing a collection, a standard collection. The repository can delegate the reconstitution to a factory behind the scenes, but it does offer a specific interface that makes sense in terms of the responsibilities of a repository at the domain level. So the process could be like this. If we look at the client, a repository, a database, and the factory and how they interact. So initially, we issue a query to the repository. The repository then queries the database. So it generates an SQL query to the database, obtains a result table. That result table is sent to the factory, maybe not directly, maybe it is first interpreted and the corresponding calls of the factory are created. However this is done is irrelevant for what we're considering here. The reconstituted object that we obtain back from the factory is then passed to the repository and passed on to the client. Factories should remain free from persistence responsibility. A factory instantiates a complex object from data, but not directly from a database. The client can use the repository to persist a new object. So the factory creates an object, but it doesn't add this object automatically to a database. So the sequence of calls could be that the factory creates on behalf of the client the object is returned back to the client. If the client then has a need to persist the object, the client adds the object to the repository, and eventually the repository or the unit of work manager inserts the rows into the database. Sometimes you might see factories and repositories combined for an operation that you could call find or create. So there is a find. If the object cannot be found, then it's automatically created in a combination of factory and repository. This is discouraged. For value objects, it doesn't make any sense in the first place because you could just use the factory to create a new object. There's no need to find or create. For entities, there is a distinction between a new or an existing object, and that distinction is relevant in the domain. Whether you are actually creating a new customer object as an entity, or whether you are finding an existing customer, those are two completely different operations from the perspective of the domain. And so therefore, they should not be lumped together into one. We're now going to look at considerations for storing objects in relational databases. There are some common cases. One would be that we have a database, and the database acts as a repository for objects for this system. Another common case could be that there is a database that already exists and it was originally designed for a different system. Yet another common case is that we are designing a database for our specific system, but it will also serve in roles other than as object store for this application. Possibly we have to consider other applications that will also need to access our database. And each of these cases impacts our model in different ways. If we have a database that is specifically designed for this system, then by implementing some model limitations, we might be able to simplify the mapping from the domain model to the database schema. The database structure can also support aggregate integrity checking when updating. So that's something to keep in mind. Does our database structure, does it help in checking the integrity of aggregates? Our table design can differ from the domain model, but it is important to understand that multiple overlapping models can cause complications. This is what might result if we have one domain model and we have a slightly different but related structure in the table design, and then developers will always have to switch back and forth between two different models, and it's quite obvious that that can cause complications. It's not necessary to have a one object, one table approach, but what is important is that the mapping from domain objects to the database tables should be easily understood. We might be willing to sacrifice some richness in our object relationships and thereby gain ease in the implementation in the relational model. This is something we might need to consider. For example, we might accept denormalization if it helps simplify the mapping. And what we definitely want to do is we want to prevent processes outside our object model from accessing the object store. And that should be pretty clear. If we allow processes that are not subscribed to our domain model, if we allow them to access the object store and to update it, for example, or to add data to it, then in that way we might end up with violations of our invariants. And on top of that, these other clients, these other processes will rely on the specifics of the database design, and thereby we will lock in the database structure, and we will no longer be free from the purpose of our application to change the implementation of the database, of the structure of the database, which we are as long as we are only accessing the database through repositories. If our database structure comes from a legacy or an external system, then we are facing a situation where there are at least two domain models, that of the legacy or external system and that of our application. In that case, a better option than to stick with those two domain models might be to conform to the other model. If it is already established and if it is useful, that might be the better option, to abandon the domain model of our application and to instead subscribe or conform to the other domain model. Another option is to make the two models completely distinct and to declare a boundary between them, to declare each one its bounded context. And we will get back to that option later. In our implementation of our domain model as a relational database, simple directness is best. What we mean by that, if we have one table row per object, possibly including some subsidiaries in an aggregate, so possibly some objects that are part of the aggregate would be included in our table row. This is normally the best option. Foreign keys in a table should translate to references to another entity, and our ubiquitous language can help tie the object and relational components together. By inspecting our ubiquitous language, you often see how the object and the relational components need to be tied together. Our names and associations that we can observe at the object level should correspond exactly to those that we can observe at the relational level. Refactoring is not as well supported for relational databases as it is for object-oriented design, and this might actually lead to a drag on refactoring the object model. If our goal is to keep the relational database design and the object-oriented design that we have hand in hand or in sync, then the fact that the refactoring on the relational model is not as well supported might lead to a drag, to a delay in the refactoring of our domain model. This concludes the discussion of repositories and of the lifecycle aspects of domain objects.